So can you see the Maple worksheet?
Yes, Professor, I can.
Okay, so let's see. So this is Math 155. Review problem 12. So the area under a curve is just the integral, right? So the area would just be the integral of seven plus 3 times the sine of x over 4 where x goes from 0 to 8 pi. That's the answer.
Oh, that was easy. Could you do problem number 14 as well, Professor, please?
Okay, so in problem 14, we have a sequence of integers. So A1 is equal to 3. A2 is equal to minus 2. And for n from 3 to 20 do, and we define the nth term of the sequence, un, to be equal to the n minus first. Sorry, calling this a. an minus 1 minus a n minus 2. So 3 minus 2, and here, A20 is negative 2. Okay?
Awesome. Thank you, Professor.
Okay. All right. Calculus questions? Algebra questions?
Well,
Any questions from calculus? Math 175?
Sir, I have a Maple question.
Well, I just did one. I just want to go cycle through different classes. What about algebra? Questions from algebra?
I have from 615.
Sorry, you have problem 6.
No. I have I'm algebra 615.
Okay.
Question number on the review, the homework 10 final exam review problems.
Yeah.
Give me a second. Okay, so number 15. 15.
Okay. Okay, so I did that in class this morning, and you can see that on the video, but I'll do it again quickly.
Okay.
All right, so algebra review. Problem 15. So the group is R2, just the ordinary XY plane. And we let H be the set of all points X comma X. So that's the same as the set of all points XY, where Y is equal to X. So we want to show this is a subgroup. So geometrically, of course, this is just the line Y equals X in the plane. Right? That's what it looks like. And you can notice that 0, 0 is in H because they have the same X and Y coordinates. So H contains the identity. And if you take any 2 points, XX and let's say YY, plus or minus, if you either add or subtract them, you get either X plus Y and X minus plus Y, or X minus Y and X minus Y. So both of them are in H. So H is closed under addition and subtraction. So H is a subgroup. And then we look at the left coset, 0, 3 plus H. So this means all points of the form 0, 3 plus X comma X, where X is in R, because that's the set of points in H. And we're just adding these two vectors. That's just X, X plus 3. Or another way of saying that, that's all points X, Y, where Y equals X plus 3. What is this? This is just the line Y equals X plus 3. It's a line parallel to H with slope 1 and y-intercept 3. So this left coset is just a line parallel to H.
Okay, thank you.
Okay. And if you looked at the left coset 2, 5 plus H, turns out it's exactly the same left coset, because on this line, you have the point 0, 3, but you also have the point 2, 5. So these two cosets are exactly the same. Right. Okay. Anyone else have an algebra question?
Hello, Professor? Yes.
Go ahead.
For the final review that you sent us, can you do questions 6, 12, and 13?
Well, one after the other. What's your first choice?
Okay, well, let me see. Then I guess go with 12 first, I guess.
Okay.
Yeah.
So number 12, we have the permutation sigma, which is 1, 2, 3, and 4, 5, and tau, which is 1, 4. So what is sigma times tau? It's 1, 2, 3, 4, 5, followed by 1, 4. Let's write that in standard form, let's say. So this sends 1 to 4, and then 4 to 5. This sends 2 to 2, 2 to 2, 2 goes to 3. 3 goes to 3, goes to 3, goes to 1. 4 goes to 1, goes to 1, goes to 2. 5 goes to 5, goes to 4, stays at 4. So a sigma tau is this permutation. If you write it as a product of disjoint cycles, 1 goes to 5, goes to 4, goes to 2, goes to 3, goes back to 1. So that's sigma tau. And you only get it right if you understand this is composition of functions. It acts from right to left. If you write tau sigma, that's 1, 4, and sigma is 1, 2, 3, and 4, 5. So this sends 1 to 1 to 2 to 2. 2 goes to 2, goes to 3. 3 goes to 3, goes to 1, goes to 4. 4 goes to 5, goes to 5. 5 goes to 4, back to 1. So this is the permutation 1, 2, 3, 4, 5, 1. So it's completely different. Sigma tau is not the same as tau sigma. All right.
All right, Professor. So right here, when you were doing it, I was a bit confused because when you go to, let's say, tau sigma, right? When you go to that line, you started with the 4, 5. You said 2 goes to 2 goes to 1. I was confused.
This is tau sigma or this? Which one are you referring to?
Tau sigma.
This.
Yes.
So this is tau, and this is sigma. And these are functions. So it's just like in calculus. F composed with g of x is f of g of x. You operate on the right. So what does this do to 1? This sends 1 to 1. Then this sends 1 to 3. And this sends 3 to 3. This sends 1 to 1. This sends 1 to 2. This sends 2 to 2. So 1 goes to 2. Yes.
Okay, so let me see if I understand that part. So since in the 4, 5, when you start with the sigma from right to left, there is no 1, so it's like 1 to 1.
Correct.
But then in the second one, 2 gets sent to 1.
No, here,
Okay.
1 gets sent to 2, 2
Okay,
gets sent to 3.
Okay. And then 2 gets sent to 3. And then let's see. All right, and then that's how you get a 2 gets sent to 3, and then 1 gets sent to 2 for the first part.
Excuse me, Professor. I'm still kind of having a hard time understanding the one being sent to, just kind of like what you just explained. I'm still having a hard time seeing it.
Okay, so think of it like this. Suppose you have f of x is tau of x. This is tau. And g of x is sigma of x. This is sigma.
Oh,
Okay?
Professor, I can't see the, yeah,
Right?
there, thank you. Mhm.
So sigma, so tau sigma of x, this is tau of sigma of x for any x. So for example, tau sigma of 1 is tau of sigma of 1. This is sigma. What is sigma of 1? Sigma of 1 is 2, right? Sigma sends 1 to 2. So this is tau of 2.
Oh, okay.
What is tau of 2? It's 2. Tau sends 1 to 4, 4 to 1, 2 to 2, 3 to 3, and 5 to 5.
Okay. Thank you.
And if you have to calculate the order of sigma, so sigma is 1, 2, 3 times 4, 5. And these are disjoint cycles, so they commute. So sigma to the k is 1, 2, 3 to the k, 4, 5 to the k. And this has order 3. This has order 2. But the smallest k that sends each of these to the identity is k equals 6. So sigma has order 6. If you start raising sigma to powers, the first time you get the identity is when you get to 6. Okay. Is there a calculus or a maple question?
Yes, sir. I have a maple question.
Okay.
I was actually hoping that you could go back over 12 because I put in the exact input that you did, and I got something completely different.
Okay, let's take a look. So you want to find the area under the curve 7 plus 3 sine of x over 4. And the area under a curve is the integral. And it says from 0 to 8 pi. So let me just write it down maybe more exactly. The area is this integral, which is equal to 56 pi, according to this.
Well, Professor, for the area that I got 12 plus 56 pi minus 12 cosine, and then in parentheses 2 pi.
Well, is this the function? I mean, Maple doesn't give different answers to the same problem. I mean, if you plot this function, this is the function, and the area is the integral. So if you write down this, you have to get 56 pi. I mean, there's no other possibility. In fact, if you look at this carefully, you'll see this is the horizontal line, y equals 7. This area right here equals this. So this integral is going to be exactly the same as the area of this rectangle, which is 7 times 8 pi, or 56 pi. So this is definitely correct. And you must have done something wrong when you enter the data. Sometimes you might have had something already on in the memory of your computer. If you go to this round circle, this thing, and you click on that, that erases all of anything you might have had in memory to screw up the result. Right? So did you get this answer?
Well, I had done what you said, and I can't see any differences at all. What I put in and what you did,
Well,
and I'm still getting the same thing.
you spell every letter is exactly the same. There's still a dot here and a capital P and a dot here.
Yes, sir. Yes, there is.
And when you write down the integral, it looks just like this. This picture is the same.
Well, no, I'm not getting 56 pi.
No, forget the 56 pi. The integral sign from 0 to 8 pi, exactly this expression. Do you see that on your screen?
Well, yes, I see the expression, but I'm not getting the 56 pi.
So it has an integral sign 0 to 8 pi. 7
Yes, sir.
plus 3 times sine of x over 4.
Yes, sir, all of that.
And I have absolutely no idea why it doesn't work for you. If I could see your computer, if we were in a lab, I could look at your computer, but I mean, if there's only one answer and Maple never gets it wrong. Tell me again what you got as your answer.
For the answer that I got, it was that exact expression with everything but 56 pi at the end.
What do you mean that exact expression? What did you get?
I got a area and then the 8 pi over 0, and then in parentheses 7 plus 3 sine x over 4, and then the dx at the end, but no 56 pi.
Wait. None of that makes any sense. So you don't see this on your screen, this integral.
Well, yes, I see everything that you got apart from the 56 pi.
So you actually see this x over 4.
Yes, sir.
And you see the dx.
Yes, sir.
And you wrote it down exactly like this.
Yes, sir. I made sure to capitalize the I in the beginning. I made sure to put every single last symbol. I just can't see when I'm not.
Do you have a space somewhere where you shouldn't have a space? Like, do you have a space after the T and before the parenthesis?
Can you share your screen if that's possible for Professor to see exactly what you have?
Did you have these kinds of problems with other problems? Like, did you do this next problem and get the same answer? This recursion?
Well, I didn't get that. I didn't copy all that down in time. I was just focusing on 12.
Well, here, calculate the integral of x squared from 0 to 1 and tell me what you get. Right. What did you get?
I'm sorry, Professor. I'm still trying to get the equation done.
Get what?
I'm still trying to put the command in.
So can you take a screenshot of your computer screen? Do you know how to do that?
He can probably share his screen also, so you can. You probably have to give him access to do that.
No, just do a screenshot and then email it to me and I'll take a look at it from my email.
Okay, Professor, I guess I'll do that.
Okay. Any other questions about Maple? Questions from calculus?
For math 156, can you do question number 2, please?
Okay, so 156, number 2, just 1 second. Just to plot 2 lines on a graph? Was that the problem?
Yeah, that one, because sometimes when I do on Maple, there's always like a command I do wrong, and I just want to make sure I'm doing it right.
Okay. So there are a couple of ways you can do it. So this is from Math 156, problem 2. So you want to plot these 2 lines together. Two x minus 9y equals 7, and 3x plus 8y equals minus 5. So one thing you can do is solve each of these equations for y. You could say solve the equation 2 times x minus 9 times y equals 7. Solve that for y. Let's call this y1. This is so that's the first line. And we could take the second equation and solve it for y. We'll call that y2. That's what we get when we solve the equation 3 times x plus 8 times y equals minus 5, and solve that for y. So we get this, and then we want to plot together these 2 lines, y1 and y2. And there it is. Another way to do it is we could use the implicit plot command. So we open the plots package. I don't need to see that. So I can say implicit plot. And let's say I want to plot these 2 lines. 2 times x minus 9 times y equals 7. And 3 times x plus 8 times y equals minus 5. And maybe x goes from minus 10 to 10, and y goes from minus 10 to 10. And again, it looks the same because we're plotting the same 2 lines. It's just that we use different commands. If you do it to scale, that's what that looks like. That's what that looks like. So that's two different ways to solve that one problem. Anything else from Math 156? What about from algebra? Anything else? Anyone have a question? A lot of people, not many questions.
Hi, Professor.
Yes, go ahead.
Yeah. I'm here to watch and learn. I don't have any particular question to ask. So I
Okay,
don't know. I'm in 156 calculus. So if there's anything you want to do, I'm here to watch and learn.
no, I'm just answering questions.
Oh, okay. All right. No trouble. Thank you.
Yeah,
Can you also do the first one for Math 156? That one kind of got me stopped a little bit. I wasn't sure how to approach it.
okay.
Thank you.
So let me go back to this. Let's see. Just to give it a name. So we want to solve a certain equation. So the equation is 12 over x squared plus 1. This is also on the Math 155 review sheet, I think. 5 plus the cosine of 2 times x plus sine of x. Equals. All right, so we have this equation, 12 over x squared plus 1 equals 5, and we want to find solutions for that. So we do f solve. Solve this equation for x, and we get one answer. Now, there might be more, we just don't know. So you can check by plotting the left-hand side and the right-hand side separately. That's one way to do it. So I'm going to graph 12 over x squared plus 1, and I'm going to graph this. And when I graph it, it looks like there are two solutions. See, the red curve is 12 over x squared plus 1, and the blue curve is this trigonometric expression. And they cross here and here. And f solve only gave me one answer, 1.1. Let me change this slightly. Let me make this from, say, x goes from -6 to 6. All right, so this, it looks like it's going to be 1.1, but there's a negative solution. So we also have to find the negative solution. And we can do that by using the fsolve command, but telling Maple to look in this region, like, for example, x going from -4 to 0. And x going from -4 to 0. And now we get this solution. So that's how I find all two solutions. F solved by itself just gave me 1, but looking at the graph tells me that there are 2 solutions. One of them is negative. So I'm forcing Maple to look for a negative solution, and then it finds it. What else can I do?
Could you go to question 6 for algebra?
Question 6 on the review sheet
Yes.
is,
Specifically B and C.
sure. Okay. So this is Algebra Problem 6. So S is the matrix 0, -1, 1, 0, and T is the matrix 1, 1, 0, 1. And for part B, we want to look at T to the N. So let's see, what is T squared? It's 1, 1, 0, 1, 1, 1, 0, 1. When you multiply the matrices, you get 1, 2, 0, 1. What is T cubed? T cubed is T times T squared. So that's 1, 1, 0, 1 and 1, 2, 0, 1. And when you multiply these matrices, you get 1, 3, 0, 1. And you want to prove that T to the N is 1, N, 0, 1 for all non-negative integers N. So this is true when N equals 1, 2, and 3. So the proof is by induction on N. Suppose for some N, T to the N is 1, N, 0, 1. So then T to the N plus 1 is T times T to the N. That's 1, 1, 0, 1, 1, N, 0, 1. And if you multiply these matrices, you get 1, N plus 1, 0, 1. You get exactly what you're supposed to get. So T to the N is 1, N, 0, 1 for all. All right, so that's a proof by induction. And how do we prove? So this was part B. Part C is to prove T to the M, T to the N is T to the M plus N for all M and N greater than or equal to 0. So let's see. Well, actually for that, that's really just there's really nothing to prove there because this is just powers of T. In every group G, if X is in G, then you have the usual rule for exponents. X to the M, X to the N is X to the M plus N. So there's really nothing to do for this part. I mean, the only part of this problem that requires a proof is part B.
Okay, I just thought there was like something else in there because I mean it's just Tn times Tn, which is just
Yeah,
T.
that's all it is. I mean, the interesting part is this.
Okay, so it was just B that was a bit, lengthy.
Yeah.
Okay. Could you also do for part A, the inverse of T?
Oh, yeah, sure. So, well, for one thing, you know that if A, B, C, D is a 2 by 2 matrix with determinant not equal to 0, call this A, then the inverse is always 1 over the determinant times the matrix D minus B minus C A. So if you let T equal 1, 1, 0, 1, AD minus BC is 1 times 1 minus 1 times 0 is 1. So T inverse is 1 over 1. So you just interchange these two and change the signs of these. So, and then you can check 1, 1, 0, 1, 1 minus 1, 0, 1 is 1, 0, 0, 1. It's the identity. And the same if you go 1 minus 1, 0, 1, 1, 1, 0, 1. It's also the identity. So, I mean, all you have to do is write this down and check that it works. Now, if you didn't remember the formula for an inverse of a matrix, you could go like this. You would say, well, 1, 1, 0, 1 times some matrix A, B, C, D is supposed to be the identity. And when you multiply this, what do you get? You get A plus C, B plus D, C, D. So that means that if that's going to be the identity, then A plus C and D have to be 1, and B plus D and C have to be 0. But if D is 1 and B plus D is 0, then B is minus D, which is minus 1. And if A plus C is 1, A is 1 minus C is 1. So you get A is 1, B is minus 1, C is 0, and D is 1. So you could just calculate it directly like that also. Anything else?
Did you go over question 23 today, or from
which
the
class?
final algebra?
No, but I'll do it now.
Okay.
So we have A, an element of a group G, and the centralizer of A is all the elements of the group that commute with A. And we want to prove this is a subgroup.
So Professor, what is a centralizer?
That's this. This is the definition.
Okay.
I mean, yeah, the centralizer is this set of elements that commute with A. So for example, if you take A times the identity, that's A, and the identity times A is A, so E commutes with A, so E is in the centralizer because the identity commutes with A. And if X and Y are two elements in the centralizer, then what can we say about X times Y? So X times Y times A is X times YA by associativity. That's X times AY because Y is in the centralizer. That's XA times Y, again by associativity. XA times Y is AX times Y because X is in the centralizer. So this is also, then this is A times XY by associativity. So if X and Y are two different elements in the centralizer, XY times A equals A times XY. So XY is also in the centralizer. So the centralizer is closed under multiplication. And suppose I take any element X in the centralizer. So AX equals XA. Multiply on the left by X inverse. Multiply on the right by X inverse. This is the identity. So I have X inverse times A, and this is the identity, equals A times X inverse. So X inverse is in the centralizer. So this says that every element in the centralizer has its inverse also in the centralizer. So the centralizer satisfies the three requirements for a subgroup. It contains the identity, is closed under multiplication, and it contains the inverse of each of its elements. Okay.
Should be able to do number 25, please?
In the algebra sheet?
Yes, please.
Okay. So number 25. So this is just like the problem we did with the sine and the cosine. So R is the additive group of real numbers. T is the complex numbers of absolute value 1. So R is just the line, and T is the unit circle.
So what's that Z and then what's that 1 for?
This-
Z,
So this is the definition of T.
Okay.
T is what the problem says. It's the complex number of its absolute value 1.
Oh, okay.
So all Z in the complex numbers where the absolute value is 1. That means the points on the unit circle.
Okay.
And we have this function f from R to T defined by f of the number T is the complex number e to the 2 pi Ti, which is the same as saying f of t is cosine 2 pi t plus I sine of 2 pi t. That's the definition of this. It means the same thing. But if you write it like this, then it's easy to see that it's a homomorphism because f of s plus t is e to the 2 pi I s plus t. That's e to the 2 pi I s plus 2 pi I t. And that's e to the 2 pi I s times e to the 2 pi I t, right? Because you always have, any number x to the s plus t is x to the s, s to the t. It's just an exponential. And this is f of s, and this is f of t. So that's the definition of a homomorphism. So f is a homomorphism.
Okay. Thank you.
Mm-hmm. Right. A couple more minutes if the other questions. Calculus, maple, algebra.
I have a maple question
Okay.
for 156. Can you do number 13?
Sure.
Thank you.
So let me get back to maple. Where is it? Okay, so this is math 156, problem 13. So all we want to do is write a program that lists prime numbers of a certain sort. So I can say the following: for n from 1 to 100, do. And I put in my n do. And what do I want to do? Well, if a certain number is a prime, I want to write it out. So if is prime, that function, n cubed plus n plus 1, then what I want to do is print it. And I have to write end if at the end of this if conditional. So that's my little program. It's just this one line. Let's see if it works. So all of these numbers are primes of this form. If I want to know what n is producing each of these numbers, let me write n comma that. So yeah. So like when n is 1, 1 plus 1 is 3. When n is 2, 8 plus 2 is 1 is 11 is a prime. Let's see, when n is 4, 4 cubed is 64, plus 4 is 50, plus 1, 51. Well, 51 is not a prime. It's 3 times 17. So 4 doesn't occur here. But there are quite a few primes of this form. Yeah. But this is the whole program. For n from 1 to 100, do. And what do you do? If this number is prime, then print it out.
Thank you. And for 14, where it says counts, you would just put the n like you just did.
For 14, yeah, so that's more interesting. So let's look at that. So this is Math 156, problem 14. I want to say, well, let's say fix this number capital N, which is going to count the number of primes of this sort. So I want to say for n from 1 to 100, do, put in my n do, if this number n cubed plus n plus 1 is prime, then add 1 to n. So replace n with n plus 1. And I need an end if. And then I need to print out my result. Let me write it like this. Print the number of primes is n. Let's see if that works. Ah, 31 of them, it says.
Thank you. And someone asked to do number 16.
In the maple?
Yes.
Oh, okay.
All right, thank you, Professor. I'm gonna head out.
Okay. I'm going to have another hour help session tomorrow at 1 o'clock.
Oh, okay, yeah, because I just emailed you. Okay, so perfect. Tomorrow, perfect.
Okay.
All right.
And I'll send out an email to everybody, but 1 o'clock tomorrow, we'll have another Zoom session.
Awesome. Thank you.
Okay, so let's see. Math 156, problem. Sorry, which one did you say?
16.
16. So there's this function rand with parentheses, and that generates a random number with 12 digits. And every time you do it, of course, you get another random number. And we want to generate 10 random numbers and see which of them is prime. So all you have to do is the following. Let's see. For n from 1 to 10, do, because I want to do something 10 times. And let's say, suppose we let a be this random number that we're generating. And then just is prime. So this should, oops, and this should be RAND. So what this program should do is produce a random number and say true or false whether or not it's prime. So there we are. For each of these numbers, false, well, any of them, yeah. All of these happen to be not prime. So, and you'll notice if I do it again, I'll get a different list because it's generating random number every time. Looks like it's hard to get a prime. Let me do it again. Again, 10 random numbers and none of them is a prime. But this is what the program is. And I have to do this sort of roundabout thing. Let A be the random number and tell me if it's prime, and then just repeat this 10 times. I had to give this random number a name. I called it A every time. I could have enumerated them. I think I could have. Let's see if this works. AN. Yeah. Yep. Ah, this time I actually got a prime. This guy, the first one that was generated happened to be a prime, but the other 9 are not. Okay, I gotta quit now. But again, tomorrow at 1 o'clock, another help session if you have any questions. Glad. And for Maple, where the exam's not until another week, I'll have several help sessions during the week. So today, tomorrow, and yeah, as much as I can.
Professor, you said at 1 p.m. tomorrow you would be having another session, right?
Yes.
Okay, thank you very much.
Okay, all right.
Thanks, see you.
All right, bye all.
Professor,
Yeah,
do you post this recording?
I will.
Oh.
Actually, I have, see, I have like a separate YouTube playlist for each of my classes. So I don't know where to post this. What class are you in?
The Maple 156.
All right, I'll post it on Maple 156.
Okay, thank you.
All right, bye.
Bye-bye.